Hello students, welcome to Sri Jendra's Rank Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 12 of a unit, electric charges and fields. In the previous classes, we were discussing about the Gauss's law and their applications. We have already done through the application of Gauss's law for the charges. I mean to say for the point charge, for the sphere, for the conducting sphere and for the non-conducting sphere. Next, we have gone through the electric field due to infinite plane shapes, whether it could be a conducting or it could be a non-conducting. Today, we are going to discuss about the electric field due to a uniformly charged infinite wire. So let's begin with today's class. Look at this. First, I have taken this infinite wire, which is having a positively charged. And previously, we have discussed that we have three kinds of density. One is the surface charge density, one is the linear charge density, and other is the volumetric charge density. So let's suppose I have given this wire as a linear charge density and that I represent as in lambda. So when I need to enclose this surface, I need to choose a certain Gaussian surface. For wire, the preferred Gaussian surface would be a cylindrical Gaussian surface. You need to remember this. We have already used three different kinds of Gaussian surface. When charges were there, when a point charge were there, I have been used a sphere. When infinite sheets were there, I have been using, what is it? Tell me, do you remember that? Yes, we are using the pillbox. And while using the wires or while using the cylinders, we need to use a cylindrical Gaussian surface. Now look at this. This is the charge is given and the charge is positive, and I have made an imaginary cylindrical surface. The length of an imaginary cylindrical surface is L and its radius is R. Now let's look what would be the flux and how could I calculate it. I know that flux is equals to E dot A, and while I calculate E dot A, it would be an E A cos theta. So if I consider this surface, this is the surface number one, this is the surface number two, and this is the flat surface, it is a third surface. So if I consider this two disk kind of surfaces, the area vector would be in this direction. As this road is positively charged, its electric field will be radially outward, and for this radially outward would be in this direction. Same is the case with the surface number 2. Area vector would be in this direction and electric field will be in this direction. Here you can see this that both are having an angle of 90 degree and cos 90 would be a 0. So flux through first surface and flux through second surface would be a 0. It cannot contribute anything. It cannot contribute anything to create a flux. Now let's talk about the third surface. The area vector would be in this direction. Electric field would be in this direction. Here, for the third surface, theta would be a 0 degree. So what would be the flux 3? E into A into cos of 0 degree. And when it is an E into A into cos 0 degree, that is E multiplied by cos 0 is 1. Area of a cylinder. What is it? It's a curved part. It's a 2 pi RL. Yes. So this is E multiplied by 2 pi R multiplied by L. This is the flux. So, so total flux through the Gaussian surfaces, flux through the curved cylindrical part of the surface, because flux through other two surfaces are already zero. So total flux, this is E multiplied by 2 pi RL. Now, I have already know this that flux should be is equals to always written as Q enclosed by epsilon naught. And when you have given a charge lambda, it is a linear charge density. I know this lambda should be is equals to Q by L, and this Q should be is equals to lambda into L. This Q should be equals to lambda into L. So I can write like this. This is lambda into L. divided by epsilon naught. So if I compare this two, this is E into 2 pi r is equals to lambda L by epsilon naught. And if I solve this, what I am having this is equals to lambda divided by 2 pi epsilon naught, where r is the distance. Yeah. Now, what I can do is, let us multiply this with the 2 and divide this with the 2. This is 2 into 2 pi. This is a 4 pi epsilon naught. This is 4 pi epsilon naught. And rather, I should say that this is 1 upon 4 pi epsilon naught. So this can represent a P. And the things will be easier to remember. This is 2 P lambda by R. That electric field for an infinite wire, I should say, electric field for a infinite linear charge density, electric field will be calculated as a 2k lambda by r. If I write this according to the vector, it is a lambda divided by 2 pi epsilon naught r into unit vector n. If if lambda is positive, let's say something look like this. A wire is there. It's an infinite length wire. It has been extended on both the sides. And the electric field will be having a magnitude of 2k lambda divided by r. 2k lambda divided by r. Its direction would be radially outward from the wire because it is a positive impact. It looks like something like this. So if wire is having negatively charged density, let's say this is lambda, then the magnitude remains the same. It is a 2k lambda by r. But direction changes. It should be radially inward. Did you get this? Are you sure? Okay, let's move on. You just remember this formulas. One more thing. You should note that only the charge enclosed by the surface lambda was included above. The electric field E is due to the charge on the entire wire. You need to consider the total charge on the entire wire. We have considered the charge on the entire wire, and what we get as a result is that is 2k lambda divided by where r is the distance. R is the distance from the wire. Are you clear up to this? Are you clear up to this? Are you sure? Okay. But do you have one of the question that, sir, this is the electric field due to an infinite length of wire. But what could be the cases? What could be the cases if if wire is of finite length? What happen at that point of time if wire is having a finite length? So you might have gone through the theory sections of this topic in the class books, but let me show you directly the results of this situation. Let's say one of the wire is given and having a linear charge density of lambda, and it has been given a positive charge. You need to find out electric field at this point. Now listen this very carefully. Listen this very carefully. What you need to do is, let's say this distance is r. What you need to do is, you need to make two lines on the ends of the wire from where you require an electric field. So let's join this as a first, this as a second. Now name the angle. Let's say this is the angle beta and this is the angle alpha. This is the angle beta and this is the angle alpha. Now I am having an electric field. I am having an electric field in two directions. This is Ex, electric field in x direction, or rather I should say is an electric field in the horizontal direction, and this is Ey. This is electric field in y direction. When I write Ex, listen this very carefully. When I write Ex, I should write as k lambda divided by r multiplied by sin alpha plus sin beta. When I write E1, it should be k lambda by r into bracket cos of beta minus cos of alpha. This would be the situation. Let me repeat this. What we have given is that we have given a finite wire having a linear charge density of positive, having a linear charge density of positive. I require an electric field at this point. I require an electric field at this point. What I need to do is first, on a very first step, you need to connect that point with the ends of the wire. You need to connect this point with the end of the wire. So on a first I did this, on a second I did this. Now give the angle names on that lines. So let's say I have given a name as an beta, I have given a name as an alpha. Now you need to calculate two of the electric fields. One is the EX, another is the EY. How could I write Ex? That Ex would be is equals to k lambda by r into bracket sine alpha plus sine beta. While the Ey, it's an k lambda by r into bracket cos beta minus cos alpha. This would be the situation. Now, if I have been asked E net, if I have been asked E net, then what it would be? Look at this. Here Ex is in positive x direction, Ey is in negative y direction. And the angle between these two is 90 degrees. So if I will be on a scalar, I should write like this. This is ex square plus ey square. This is ex square plus ey square. This is the final answer. This is the final answer. Yes. Shall we do a practice of this? Did you remember this? Do one thing. Take your book, have a paper and pen, and just write this relations ex and ey because we are going to solve the numericals based on this only. So we require this formulas. Ex would be equals to k lambda by r into bracket sine alpha plus sine beta, and Ey is equals to k lambda by r into bracket cos beta minus cos alpha. Have you did this? Okay. Let's start the numericals. On the very first application, let's assume that this is a wire which is infinitely long, which is infinitely long, and at this point, at this point, you require an electric field R. You require an electric field at point P, which is at a distance of R. Now, what should be done? Tell me. A first situation would be make an angle. Make an angle. So, if this wire is infinitely long, look at this. Let's first try to understand. If wire ends up here, I need to connect this line as this. But you say, no, sir, wire has not been ended at that point. It is ended at this point. So let's make a line like this. You said no, sir, wire is still there. Wire is still there. So you need to increase your angle. So let's say I have increased my area to this. You said no, no, sir. It is still there. So if you can observe this, this is theta, this is theta 2, this is theta 3. My angle is increasing. So if I need to match with the infinite wire, I need to do a parallel line. Can you understand this? If I need to match with the infinite length of wire, I need to have a parallel line. And when I make a parallel line, that means my angle would be 90 degree. So let's say this is an angle of 90 degree. Here the case would be the same. Here even it has been extended up to the 90 degree. So even this would be the 90 degree. Now Now, I have been decided the angles. I have been decided the angles. Now, what next? The next would be the EX and EY. My EX would be in this direction, EY would be in this direction. What is EX? I haven't said that it is k lambda by r multiplied by sine of alpha plus sine of beta. Now, this is k lambda by r multiplied by sine alpha. This is 90 degrees. That is sine 90 plus sine 90. This is 1 plus 1, 2. That comes to 1, 2 k lambda divided by r. This is Ex. When I talk about the Ey, when I talk about the Ey, it is a k lambda by r into bracket cos beta minus of cos alpha. So that should be k lambda by r into bracket cos beta minus cos alpha. This is cos 90 minus cos 90 would be a 0. So if Ey would be a 0, Ey would be a 0, E net, E net would be equals to 2k lambda by r. Look at this. This is perfectly matching. This is perfectly matching with the relation that we have derived it with the help of Gaussian law. Yes, so it means I can use this relation. This works perfectly fine. This works perfectly fine. So let's begin journey. Let's say, so this is what we call as an electric field due to infinite length wire, but using an applications of finite length wire. Now let's look a semi infinite wire. Did you understand the meaning of semi infinite wire? Are you? No? Let's look. Let's say this is wire. It has been terminated at this point, but it is being extended to the infinite. It is being an extended to the infinite on an upper edge. And you need to find your electric field. At this point P, this is distance. Semi-infinite wire, you need to find out electric field at point P. What should be done? Tell me. If you observe this very carefully, if you observe this very carefully, you know that this angle would be a 90 because it extends to a 90 degree. It extends to an infinite, sorry. And this angle, it is on the same line. So this angle that I have given in my image in alpha, it would be in 0 degree. This is beta, which is a 90 degree. And this is alpha, which is a 0 degree. So what should I do next? I should put it up into the numericals formulas. Ex, that is equals to k lambda by r into bracket sine alpha plus sine beta. When I replace the value sine 0, what is it? Yes, you are right. Sine alpha will be a 0 and sine beta, it's a sine 90, sine 91. So that stands to a k lambda by r. Now, now, what is E1? What is E1? It is a k lambda by r into bracket cos beta minus of cos alpha. So it is a cos 90, which is a 0, which is a 0. So this is k lambda by r into cos 0 will be a 1, but it is a minus 1. So now let's make the direction of Ex and Ey. This is the Ex, direction of Ex. This is the Ey. Yes. Now look at this Ex and Ey. Both are having same magnitude. I'm talking about the magnitude. It's a k lambda by r. So while I'm making E net, that would be root of 1 square, that means Ex square plus Ey square plus 4 into cos theta. That will give me root 2 k lambda by r in magnitude. Root 2 k lambda by r in magnitude. And what about the direction? It will be in this direction. This is the direction of E net. What was your answer? Was it same? Was it great? Let's do one more question. This is a road having a charge density of lambda, and its length is 2l. Now, from the midpoint, you have a point P, and this is at a distance of l. This is at a distance of l. You have been asked that find electric field at point P. Find electric field at point P. What you will do? What is your first step? Yes, do it. That you need to connect these two wires. Connect this point with the end of the wire. This is what I have been done. Now next task. I need to make an angle. Now look at this carefully. As I said, this is a midpoint. So this length would be the L and this length would be the L. As this both are the L, as this both the lengths are L, when horizontal distance is L, so this angle would be a 45 degree and this angle would be a 45 degree. Are you sure? Okay. Next task. I need to write down the EX and EY. So what is EX? Do this in your book as well. It is K lambda by R. Here I is the distance which is L into bracket sine 45 plus sine 45. While I write sine 45, it is 1 by root 2 plus 1 by root 2. That comes to an 2 by root 2. So this is 2 by root 2 multiplied by k lambda by L, which comes to an root 2 times of k lambda by L. This is Ex. When I write Ey, when I write Ey, it is a k lambda by L into bracket cos 45 minus of cos 45, and that comes to an 0. So this is E net. This is the E net would be equals to root 2 times of k by L into lambda. If I need to replace the lambda, if I need to replace the lambda, I can replace this at q by 12, q by 2, and this will be the answer. Root 2 k q divided by 12 square. When you can further replace this is root 2, this is 2, and you can cut it down. But one very, very important thing is, let's look at the directions. Let's look at the directions and come to the conclusion. This is Ex. This would be the Ey. But as Ey would be a 0, this component would be a 0. So only Ex would remain. Now this is the situation. Please do remember my words. This is the situation every time. Every time. When these angles are the same. And this angle would be the same. This angle would be the same. At that point of time, Ey would be converted to 0 as always. So on a rough basis, you can remember that if if a location is of midpoint, if a location is a midpoint, for which at that point you need to require an electric field. In this situation, your Ey would be always 0. Don't bother about the Ey when your angles are equal. If they are equal, you do not need to bother about the Ey. You just need to bother about the Ex, and the things will be done. Do you understand what I mean? When two angles are equal, when two angles are equal, that means my alpha and beta having the same value. And that situation, you do not need to bother about the Ey. You need to just calculate. You need to just calculate the Ex and things will be done. Let's look at the next question. Do you find this interesting? Yes. Okay. Do you find this as a difficult one? No? Okay. Let's move on. Let's say a wire is given. This is an infinite wire that has been extended from infinity to infinity, and you require an electric field at this point. You require an electric field at this point, and this is a distance r. Let me find out electric field at point. So look at this. For an infinite wire, this could be the midpoint. Anything could be a midpoint for an infinite wire because this has been extended from positive as well as this has been extended as a negative. Even you can consider this as that for this angle would be a 90 degree. For this angle would be a 90 degree. Even for this angle would be a 90 degree. Here two angles are equal. Here two angles are equal. Alpha is equals to beta. And when alpha is equals to beta, as previously said, we have Ey as a 0. We have Ey as a 0. So that means we are having an only Ex. What is the value of Ex? Tell me. Yes, you are right. It's a 2k lambda divided by r. In which direction? In positive x direction. In positive x direction. Now let's look at one more numerical on the same slide. Let's say this is a linear charge density but having a negative of charge. This charge is lambda. This is again charge is lambda. Even it has been extended. Even this has been extended from infinity from infinity to infinity. And you require to find out the electric field at this point. First, make an angle. This should be a 90 degree. Even this would be the 90 degree. Both are having a same angle. Both are having the same angle. And when their angles are equal, when their angles are equal, I mean Ey would be a 0. Ey would be a 0. So I need to bother about the Ex only. What is its magnitude? It's a 2k lambda by r. It is absolutely correct. Now, tell me one more thing. What is the direction of the Ex component? What should be the direction of Ex component? Let's do this very carefully as this is having a negatively charged road. This is having a negatively charged road. And when it is having a negative charge, when it is having a negative charge, direction of electric field will be direction of electric field will be towards the wire. So this would be the direction of electric field. This is the X. Did you understand these things? Are you sure? Okay, let's move on to the next question. This is wire having length 12. This is another wire. This is having a length 12 as well. Here midpoint is then. Let's assume it at this location. At this location, it is approximately midpoint. If I mark this, if I mark this as this is the distance and this is the distance. At this point, at this point, you require an electric field. How can you do this? How can you do this? They have been asked that find electric field at point B. Now tell me what could be done. What you need to do is give it the number. This is my first wire, this could be my second wire. Now first tell me what would be the angles. If I make an angle, this would be a 45 degree because this is L, and as this is a midpoint, even this would be the L, this would be L. And even this would be the 45-degree to me. So as my angles are equal, I need to take a tension of EX only because my EY would be the zero. Because my EY would be the zero. Now I need to bother about the EX only. Now what is my EX? What it should be? What should be my EX? If I write this, it's a EX1 that is equals to K lambda by R. R is the distance. Now in this case it is L multiplied by sine alpha plus sine beta. It's a sine 45 degree plus sine 45 degree. So this is 1 by root 2 plus 1 by root 2. This is 2 by root 2. This is K lambda by L. This is dt cos of K lambda by L into 1 by root 2 plus 1 by root 2. This is 2 by root 2. So that stands to a root 2 multiplied by K lambda by L. This is electric field due to first law in this direction. In this direction. This is electric field due to first law. Now let's find it out electric field due to a second wire. What would be the situation? I think situation would be the same. Can you guess it? Let's say this is 45 degree. Even this is 45 degree. The angles are the same. The angles are the same. And when the angles are the same, you need to when you need to worry about the EX or this is EX2. So the, all the data would be the same. It's a K lambda by L multiplied by sin 45 plus sin 45. Which will give you a 2 root 2. And that will be equals to root 3 into K lambda by L. So this should be the direction of electric field EX2. Now, now you have two vectors. One is the EX1, another is the EX2. The situation looks like this. This is EX1, this is EX2. These two vectors are there, and both are having the same magnitude. Both are having the same magnitude. So, in a case of electric field, or in the while we are doing the questions of the Coulomb's law, we know that when two vectors are having the same magnitude, I can write E net as a root of 2 into E into cos of theta by 2. Have you remember this? Have you remember this? Yes, very good. So that should be root 2 times of electric field. It is a root 2 multiplied by K lambda by L multiplied by cos theta. Here theta is 90, 90 by 2, cos 45. Cos 45 is 1 by root 2. This root 2 gone. And the final answer remaining would be root of 2 K lambda divided by L. This would be the final answer. Yes, will you be able to solve this? Are you sure? Did you? Let's look at the next question. I have been asked that find electric field at point P. Things would be something like this. Four roads are there, which are having an equal positive charge density. Let's say linear charge density we call as a lambda to be just one. And there is a midpoint. There is a midpoint. We can call it as a P. I require electric field at this point. I require electric field at this point. Now think it very carefully, but do it fast. Yes, what does came to your mind? What can I do? What can I do? My first conclusion should be for every case, EY would be a zero. Are you agree with me? Let's say this is first wire, this is second wire, this is third wire, this is fourth wire. For whatever, for whatever I make an angle, my alpha and beta would be the same. So when my alpha and beta would be the same, when my alpha and beta would be the same, I know that EY would be a zero. Now I need to take attention of EX only. But tell me, the value of EX for every case, the value of EX for every case, would it be same or different one? Let's look at it. Let's look at this. Suppose this is the distance x, and as it is a midpoint, this must be the x. This must be the x. If I make an angle from point P, this would be a 45, and this would be the 45. This both the angles would be a 45 and 45. Are you sure? What would be the situation for second wire? I hope you can understand that. This is the same. This is the 45, 45. Same is the thing for the third wire, and same is the thing for the fourth wire. So I know that magnitude of Ex. I'm talking about the magnitude. Will be for all segments. So the situation would be, I need to redraw this. Let's look at the situation again carefully. This is the situation, right? We require an electric field at point P. Now, on a very first case, you know that EY would be a zero. So that task has been done. And on the next task, I understand that magnitude of EX will be same for all the cases. I have given this as a first, this as a second, this as a third, and this as a fourth. What would be the situation? This is the direction of EX. Yes, this is true. For this radially outward means in this direction. This is the direction of EX2. This is EX1. This is the positive charge of for this, which is EX3. This is the fourth, and this will be the direction of EX4. So this vector and this vector are having an opposite direction but having the same magnitude. So this will cancel out each other, ex2 and ex4. This vector ex1 and this vector ex3 both are having again same magnitude. I can write like this, ex1 is equals to ex3. They are same in magnitude, and ex2 and ex4 are same in magnitude. So what I can write is E net would be equals to 0. What was your answer? Was it same? Are you sure? Well done. Would you be like to do a one more question? Let's say something different. Suppose you have been given uh, you have been given that this is the positive, this is positive, this is negative. Now it seems interesting. This is negative. The linear charge density having is lambda. This is lambda. This is lambda. This is lambda. But these two are negative and these two are the positive. You have been asked that. Find direction of E net. You are interested at this point of time only in the direction of net electric field. Now, how could you think this? How could you think this? Now, on a very first note, you know that EY would be a zero because this is a midpoint. Now you understand all the stuffs that alpha would be and beta would be the equal, and you need to consider only the EX case. So EY would be a zero. Let's give the numbers. This is first wire, second wire, third wire, and fourth wire. For the first wire, look at this. This is the positively charged wire. This is positively charged. So what I need to do is my direction of electric field. My direction of electric field will be radially outward. So this is the direction of electric field due to first wire. Now look at this third wire. This is having a linear charge density but in an opposite manner. It's a negatively charged density. So direction of electric field will be towards the wire. This would be the E3. Now let's consider about the fourth wire. It is a positively charged. It is a positively charged. So I draw it at this point. This is E4. Now consider the second wire. It is a negatively charged. And it is a negatively charged. And it is a negatively charged. This will be E2. So what would be the situation? The situation look like. Let's say this is point P. Here, a two vector is there which we call as an E4 plus E2. Here, again, two vectors are there which we call as an E1 plus E3. And if I consider the direction of E net, if I consider the direction of E net, this will make this. This is E1. So if I write this like this, so electric will be in southeast direction. Electric field, net electric field would be in southeast direction, or we can say it is in the fourth quadrant. If I need to be write it down in a terms of I and J, then that should be certain x minus certain j, because here I am interested in only the direction. Here I am interested in only the direction. But for a practice purpose, you can find it out. You can find it out the magnitude of the same, and that will make you practice once. Please do this. You also need to find out the magnitude of this. You will have a fun. Yes. Let's move to the next numericals very quickly. Suppose next you have been given a very long wire having a linear charge density of lambda here at point P and at a distance r. One small charge Q has been placed. You need to find out electric force on charge Q. You need to find out electric force on charge Q. Now tell me, how can you do this? What would be the situation when you need to find out the electric force? Did you remember the previous class? Do you? We have written that when I need to apply a force, I will think like this. F should be is equals to Q multiplied by electric field. And in that case, charge will be mine. Electric field will be from someone else. So here who is mine? It's in charge Q, yes. And here who is someone else? It's a wire. It's a very long wire. And when they say very long wire, they mean to say Consider this as an infinite wire. When they say it's a very long wire, they mean to say it's an infinite wire. Now, what is the electric field? What would be the electric field due to infinite wire? Yes, you assume it correctly. It is 2k lambda by r. So let's rearrange this 2 multiplied by k multiplied by lambda multiplied by 2 divided by distance. This is force acting on the point charge q. This is my answer. Yes. So let's wind it up here. What we have gone through is initially we have started with the application of Gauss's law. It's a third application that you need to find out the electric field due to infinite wire, and then we move to the finite length wire. We have gone through examples. You please make a lot of questions on this. You will find, I'm sure for this. So please do this. Take care. Goodbye. Thank you.